So I decided to make my talk a little bit more empirical, but I realized from the morning session, actually, it's hopefully quite complementary to the things that have been said. So hopefully this will be food for thought right before your lunch. So what I'm going to be talking about today is language model scaling and some connections to pre-training data. So just to set the background and to make sure we're all on the same page, why are we talking about language models in the first place? They're not really, I think, abstractly the most interesting mathematical or theoretical objects. I think many of us are thinking about them because they work incredibly well, right? And what has driven, performance improvements in language models? Of course, there's a lot of components to this, but I think a really big part of this has to be, compute scaling over the past decade, right? So, when you had something like GPT-2, it was very much a funny toy that generated a bunch of text. But I think the empirical reality has been that if you scale this up with a ton more pre-training data and compute, then you start to get much more interesting things. And just in the last, last few months, people have been talking about inference scaling, the reasoning, and these things. And I think this has really driven capabilities, which in turn, I think has led us to think about these objects. And so this has been one of the things that has really interested me, like what is this scaling? And I think an important part of this is to think about where is this field also going, right? Not just where we are now, but where we'll be in a year or two at the very least, right? And I think we have some really interesting things happening in the field now. GPT 4.5 just got released. And I think in some ways it's sort of not quite the end, but the end of a phase where every new base pre-trained model release is just amazingly better, right? I found it funny, that GPT 4.5 in their own sort of like model card says it's not a frontier model, right? And I added this little snarky remark, but it is 35 times more expensive, right? And there's been lots of discussions, I think, by people at these frontier labs talking about the end of pre-training. So I snapped this from Ilya Sutskever's Test of Time Award talk, where he's saying, oh, pre-training as we know it will end. And he has quite the way with words. He says data is not growing; it's the fossil fuel of AI. And so this is really, I think, a very intriguing thing. And I think if you've been in the field only as long as LLMs have been scaling, you kind of tend to forget how weird the situation we've been in is. Because I think if you think about statistical machine learning, really the foundations are about how do we learn well from data. It's about often sample complexities. But I think LLMs have really been very much about computational, even systems complexities, because the amount of data that we've had to bring to bear on these tasks is enormous, right? So pre-training, you've got tons and tons of data on the internet, and so you've got more data than you can even process on your very large GPU cluster. And so when you're in this regime, you often don't really even think about the relevant data components. You can just get more and more and more. But I think the previous slides show, and I think many people have been making sort of forecasts of what is the rate at which compute is growing and what is the rate at which new data is being added to the internet. And I think there's a projection right here by Epoch AI, which is I think very interesting, where they were saying the amount of data being used to train these models, they're growing very, very rapidly. That's the blue line here. And conservative or not conservative estimates of the text on the internet is this like light green line on top. And you kind of see that they're going to meet fairly soon into the future. They predicted something like 2028. Depending on what you're thinking, that might happen sooner rather than later. And I think a thing that I think is going to throw even more of a wrinkle in this, right, is that the high quality data is all trained on, right? Like Wikipedia, Stack Exchange, all these resources, they get trained on first. And so as you increase your pool of pre-training data, the quality of the data that you're training on is probably, or at least the ease of use of that data is very, very rapidly growing. Other people have said, the amount of public data is limited, but maybe we can then train on, proprietary data or data that's harder to use. Maybe we can extract information from videos, but this is all very much kind of speculation. And so what I've been thinking about, one of the things I've been thinking about is, this sort of future of more data-bound language modeling sort of seems like it's going to happen. And that's going to probably change how we're going to think about these problems. Instead of thinking about compute efficiencies and CUDA kernels and all these things, maybe we'll go back to some exciting, research and thinking about data efficiency and inductive bias and all of these things, right? And so I'm going to talk about one very basic but hopefully interesting line of work in this sort of data efficient direction. The second thing I want to talk about is the new exciting scaling axis on the block, supposedly, inference scaling. And I think there's been this narrative, especially from folks in the industry labs, basically saying, okay, maybe we've, completely mined out on pre-training scaling, but that's okay because we've got this new kind of scaling called inference or test time scaling, which will keep pushing performance upwards. But what really frustrates me, and this kind of goes back to Encore's first couple slides, the industry folks don't really tell us what's going on. And there's really no documentation of what this even is. So I've taken two examples of inference scaling plots that exist in the wild from a large pre-training lab. The left one's from OpenAI's O1 blog post. This one was really striking to me when it first came out. It shows test time compute on the x-axis in log scale. So they've got tick marks but no numbers. Why? I don't know. And then you've got performance going from 20 to 80. I mean, this is remarkable, right? You've taken a model potentially at 20% AMI performance, and you've made it think for longer, many orders of magnitude, and gotten the model that gets at 80 on 80. And I think this really captured my imagination because I think I was, in general, very skeptical about a lot of new language modeling things. But this is a very amazing plot. And also, I think I got fired up because who publishes plots without axes? I talked to some people who are very secretive in industry labs and thought we never even thought about removing numbers from axes because it's so transgressive, right? On the right is DeepSeek's R1 Lite preview. And the other frustrating thing about this one's got axes on the plot or numbers on the axes, but this one only exists as far as I know in a tweet from DeepSeek. Their final report never mentions this plot nor how this was generated. So despite the fact that DeepSeek's quite open and I love them, I have no idea how this plot was generated, right? And so we have two examples of, I think, what are very striking test time scaling plots. I have no idea how these were generated, how we can replicate them, any of this, right? So I'm going to talk a little bit about that aspect of things in the hopes of getting some clarity. So I'm going to go in the reverse order of how I presented these things. The first thing I'm going to talk about is inference time scaling. What is it? Can we get plots that look like the O1 blog? And this is actually with quite a few really amazing collaborators, Nicolas, Zitong, Weijia, and Lisa. Weijia and Lisa are final year PhD students in the job market, and quite an intimidating list of neurons. Okay, as I said before, test time scaling is claimed to be the future. And I think the way that often people talk about this, and I think this is the one thing that I think is quite misleading that I want to try to push back against in this talk, is that I think the usual way that this is framed is that, okay, well, we've got this new scaling axis where what we're going to do is we're going to deploy a model that thinks harder at test time, almost like AlphaGo. It's going to search and do all these things, and that's going to solve new problems. But I think that's not going to be the case at the end that I'll show you. So to get there, I'm going to give you, the one slide background into scaling laws and scaling. So when people say scaling laws or scaling, what does that mean? I think the object that's interesting here is essentially predictable patterns in the behavior or the improvements that a model has. And so this is probably the earliest plot of this kind. From Hessness et al. In 2018, where they argued if you train deep neural networks and you increase the data set size, you should see something that looks like a sigmoid, where you start from best guess, you have a nice power law region, and then you approach irreducible error. And empirically, the argument that people have made and has been empirically fitted and I would say, verified in some weak sense is this relationship, right? That the error that you see is some polynomial function of n, where n might be your compute power, n might be your data amount, n might be your model size, plus some irreducible error c. And so when we talk about scaling, I think we should be looking at two objects, right? We should be looking at the exponent, what is the efficiency of our scaling axis, and what is the asymptotics of this object, right? How many flops can we put into the scaling axis before we hit essentially the irreducible error of this approach? And to give you some context, right, pre-training has been the way that language models have been really powerful. And if we think about what these two things are, alpha is actually surprisingly efficient. It's out like about 0.2 if you're looking at log losses, and x-axis is compute, which is pretty remarkable because if you expect something like non-parametric rates, you get these exponents. You expect these exponents to be really bad. And then the other thing is the order of magnitude on which you can scale has been really large. I actually looked this up right before the talk. But from GPT-1 to DeepSeek V3, that's a 2 times 10 to the 5th difference in relative compute. And so it's been really, you can put a lot more compute and you get very predictable gains with the same exponent. And that's kind of the remarkable thing that I think has driven improvements. And so can we see the same thing with inference time scaling? I think that's kind of the question. And so with that context, we can kind of cast this O1 test time scaling plot and try to understand why this is interesting, right? We see lots of tick marks. I don't know what basis, I'm so sorry, in this here, that's many orders of magnitude scaling. So we expect predictable long gains. And this is relatively efficient, hopefully, when compared to pre-training. Same thing is true of this DeepSeek plot, right? But here you actually know the efficiency because you can look at the axis numbers. And so it would be nice if we could really understand what's behind these plots. And the other thing that I'll contextualize this with, and the reason why I think this is interesting, is right after O1 came out, once again, Epoch AI did some pretty interesting work comparing just O1 preview versus taking the best model at the time, which is 4.0, and then just doing some majority voting or having the model try to revise its own answers, right? Those are obviously ways of spending more inference to try to get better answers. They don't really move the needle, right? So this is qualitatively quite different scaling behavior. And so because we don't know anything about how the O1 training process was done, we can't really replicate the process, right? I mean, we can replicate the R1 process now, but at the time when we started, we really had no idea what to do. And so, but really, I would argue that what we care about is the phenomenon, not the process. And so my goal here, that I sort of originally posed to my students was, can we basically make these two plots, right? Like one plot where we have predictable test time scaling that looks like this, and another plot where we show the majority voting is much worse, right? And if we could attain this with similar y-axis range, I would consider that we have some understanding of this particular phenomenon. And so one of the things that, we tried many, many different things, but as with many things in language modeling, it turns out the simplest and sort of least technically involved thing worked the best. And so I'll describe that to you now. So what we did was we took a bunch of existing data sets for math, Newman and math. So that was the majority of this, plus some of our own data. I think one of my students, and Emmanuel, was kind of interested in, can these models do the Stanford statistics qualifying exam? And so that's somewhere in there. So we built this relatively diverse, large math data set. And then we filtered it down to 1,000 different questions based on some criteria about diversity and difficulty. And the first finding that we have, maybe unsurprising if you follow this kind of line of work, is to say, actually, we don't really need reinforcement learning at all to get models to think longer, right? So we take those 1,000 questions, we get thinking traces at the time from Gemini flash thinking, so a different thinking model. And then we just fine tune on that very long thinking trace. And the resulting model, which is this S132B at the bottom here, it gets dramatic improvements over Quen Instruct, which is where we started. We started here at 26% Amy, we go to 56, and you can sort of compare all these numbers. They're dramatically better. So the first thing that this shows, which I think is an interesting thing that you can take away, is when you think about reasoning. Oh, yes.
Just a quick question. Why did you start with an instruct model for Quen and not the base?
That's a good question. I think we started from the instruct model primarily because we didn't want to mess too much with post-training. And we were able to keep some of the instruct sort of properties by just sort of doing some replay of instruction tuning data. Okay. Also, the other thing that's kind of tricky is the base models these days aren't also base models because they do a lot of this thing called mid-training. And so at this point, it's kind of unclear what the boundaries are and stuff. Okay, so going back to my comment, so I think what a lot of the reasoning model discourse has been about is about the role of reinforcement learning, right? And doubtlessly reinforcement learning is very important because if there was no reinforcement learning, then we wouldn't get Gemini flash thinking. And without Gemini flash thinking, we can't distill out, these long reasoning trees. So RL is clearly important. But I think what this does tell us is that the reinforcement learning doesn't need to be on policy, right? So by on policy, I mean, I don't need to have reinforcement learning on my own model. RL is a way to generate supervision. And once I have these long thinking traces from even a different model, I can actually learn that and I can use that to get better performance on all these tasks. So that's the first thing. But I think many others have been doing this like O1 replication where they, make models that think better. But I think to me that it was the scaling component that was more interesting, because if a model scales, then we have hope that maybe it will continue to improve. And we tried many things like search and so on, as did others. But the thing that ended up working the best is, once again, the dumbest thing, which is, we have a target length of the thought. So we want to think for, let's say, 10,000. We run the language model, and if the language model attempts to terminate by emitting an end of thinking token before our target COT length, then we suppress the end of thinking token and we just output weight, right? And that just sort of primes the model to keep going. And then we repeatedly append weight until we hit sort of our target EOT token. If the COT length goes above the target, we immediately terminate and we put in an end of thinking token. So we like stop the model essentially mid-sentence even. And then we force it to emit an answer. And that gives us, perfect control of the COT. So this is just sort of originally almost a baseline that we tried. But this gives you almost what looks like the O1 plot. And what we see is, this is the original model that we fine-tuned right here. Basically, early termination gives you the left half of this plot, and then thinking for longer by 2x, 4x, and I think 5x is the peak, 6x gives you slight but actually pretty consistent improvements in performance. And then, when we compare to majority voting, we see exactly the same kind of plot that we saw again. So in some sense, this is sort of hitting our target. We said we wanted to get these two plots, and we got these two plots. But I think, I'll pause here and say, this is a pretty disappointing plot, because what I was hoping was we would take a model that was down here, and I would make it think for really long, and I would get over here. But what we actually found was we got a model that started out here, and then, we can go a little bit up, but that really asymptotes quite quickly. And most of this plot is actually terminating the model's thinking early. So this is much closer to like inference optimization and early exit, if you're familiar with those terms, than actually making a model think for longer. So to me, this was a little bit, honestly, of a disappointing result. And I'm still really waiting to see essentially the version of this where you start here and you go up here. I don't think I've quite seen something like that in the literature. Yes.
So the long thinking is only injected during the testing time, but have you ever tried creating longer COT data set by injecting the, let's say you collect the COT from the Gemini Flash, then you replace the output of the thinking with weight, and you can re-prompt the Gemini Flash. And you can get longer and longer COT even from, so have you tried distilling longer COT from the?
We haven't tried distilling the longer COT, although we did mess with the prompts to get longer and longer COTs. I think one thing that's hard there is, I think there you'd also run into this, because when your teacher model, when you're forcing it to think for longer, there's no supervision there either. So I think you need some external source of supervision, maybe like RL kind of thing, to make it get longer, but then you're kind of back in the same situation, I think. Oh, sorry, there were questions over here. Yes.
Is it possible that if you increase the thinking time, you might turn a correct answer to the wrong answer?
I believe that's kind of this plot. So this is one of the interesting observations, maybe more of a side note. Originally, we tried rejection sampling because we thought, oh, the right thing to do is the rejection sampling that gives us the right conditional distribution. That's really terrible, because it turns out that for a given prompt, the longer COTs are actually worse. And so there is something here that is important about like the appending weight, basically changing the conditionals to get longer COTs, because just the naively long COTs often actually, the model thinks gets the answer wrong. There is definitely that phenomenon happening, and it's quite subtle. Yes.
So from my understanding, you're using Brand 2.5 for fine-tuning the model, but 2.5 already has been fine-tuned these algorithms reasoning. So my question is, when you're saying that power scaling is not that effective, I guess maybe it's because brand direction is already relevant to the task at hand. So what happens if I use a model that's not being I don't find it in the first place? If I use a model that's very direction that are not so relevant here, downstream that.
Yeah, I think that's a good question. I think precisely formulating what the underlying scientific question there is difficult, because you would have to go back pretty far to find a model that's not RL trained. Like even like Llama 3, is going to have RL post training as part of it.
But these models have been fine-tuned for reasoning, but they have not been
maybe my point is that that's been part of post-training for a long time now. So like if you want to separate like the new test time scaling reasoning versus the old post-training stuff, then really I think the qualitative distinction has been the focus on longer COPs and the more recent post-training. Qt 2.5 does not have that, although QWQ does. So I think that's maybe the line that I'm drawing. I think if the line you want to draw is like RL or not, then I think you would probably have to take like a base model and then do no RL and do this. I think that's interesting, but maybe slightly different than the question that I was trying to answer here. So the two other interesting observations, I've already talked about the left plot here. This one is that actually it's not just about the length, because if you just rejection sample, the longer COTs are worse than the shorter ones. The other thing that we did, we spent a lot of time trying to get search to work. The search stuff does work, and it does complement, essentially our weight token approach. So you can get better performance, and then you can apply search, which is this dark blue line, or you can do majority voting. You can get a little bit more of a juice out of this, but neither of them have kind of the same sort of rate of improvement that sequential scaling does. So I think it's a pretty big open question to me how you sort of get past here and get much better performance through the use of more compute. So what's the point here? I think as far as I know, I have not yet seen any evidence of something that looks like AlphaGo style search, right? At test time, you expend hundreds to thousands of times more computational power and you get smarter models. What we have seen is, we know reasoning models work, right? This is not the point of the talk. What they do work is because, essentially we figured out even better ways to post-train. So there's better ways of, at the end of the language model training phase, use RL to get better long COTs that improve these models. That's at least my mental model. And I think it's going to be kind of interesting to see whether this is possible. I feel like this is the big challenge question for this inference time scaling steps to say, at test time, can you go way beyond the computational budget of what you originally trained with? Okay. So that was the first part on inference scaling. And the second part, I want to talk about pre-training. So go back to the other side and say, is it possible to do much more data efficient pre-training? And this is, going to appear at iClear. It's joint work with Zitong, Neil, Shangping, Emmanuel, and myself. So the setting that I think will be increasingly interesting is the more kind of statistical setting, where we're going to be in a data constrained world where we have more compute than we know what to do with. And so we need to really get as much as we can out of our very fixed amount of data. And of course, I'd like to answer this without doing large scale pre-training because I don't have the compute to be doing pre-training from scratch all the time. And so our sort of model system, which I think is a nice one, is to essentially do continued pre-training. So instead of training a model from scratch, what I'm going to take is a pre-trained model in a small domain of knowledge that the model doesn't already know. And then I want to essentially do continued pre-training, some pre-training like procedure, such that the modified model M, after this process, can do things like QA or summarization as if it was trained very well on this small specialized domain of knowledge. So the parameters have to contain the knowledge within that domain. And so this is not technically like a entirely new setting. So there's domain adaptation via continued pre-training, but I think this has exactly the property that I was saying before, which is that this is very data inefficient. So many of the examples that have been successful, essentially use something like 15+ billion tokens in order to work out, right? So this is not really something that we want. Ideally, what we want to be doing is to be able to do this with significantly less data. And so our setting that we're going to consider, we're going to take a couple hundred books and articles that are obscure enough that models don't know very well. That constitutes about 1.3 million tokens and about 10,000 times less data. And if we can do pre-training style learning that learns from this, then we might have a hope that we can have dramatically more data efficient learning methods. And so what's the problem with the standard approach? Well, the standard approach is we just do autoregressive training, right? And Conrad was telling us about how this is a terrible idea, and I think it has really bad sample complexity properties. Many of you may have heard about this reversal curse thing, where essentially if you train in one direction, you don't necessarily have the model able to use knowledge in the other one. So for example, if I have what does synthetic CPT do, and I train on this passage here, synthetic CPT appears before its definition, so the model can answer this very well. But if I'm going in the reverse direction, what method synthesizes a large corpus, trying to use sort of the suffix to get the prefix back out, then the model doesn't know this knowledge, right? It's very sort of shackled by the training order. And so if you try to actually do just continued pre-training on our small corpus, and you do it on llama 3, you start at llama 3, you do continued pre-training, you just get kind of bad performance. The model doesn't learn anything, it starts to forget things, you get this dark green line over here, even if you mix in pre-training data to mitigate forgetting. So our idea here, once again, it's a very simple, naive one that happens to work. Our thought process is, we know that pre-training already works, right? And why does pre-training work? Pre-training works because you take a piece of knowledge or take a piece of data, and it appears in many different formats on the internet, right? A single fact appears on Wikipedia, on Stack Exchange, and discussions on Reddit. And then you train on all these diverse presentations, and the model kind of knows the facts within. So the goal here is to replicate the diversity that we see in pre-training, and we're going to use an augmenter model to vary the content, the style, and sort of just generally get diversity. And once we do that, we want to mimic the process of pre-training. And if we can do that, we might hope that we can get models to learn knowledge from small amounts of data. And so the V0 of this is to just have the model paraphrase the data that we have. And even that baseline actually is remarkably strong, where we rephrase a few hundred textbooks, and we rephrase repeatedly, many times, to tens to hundreds of millions of times. And we see consistent gains in sort of the QA performance of the model, where this y-axis is answering questions about those books. But of course, this is pretty slow, and it's going to take quite a bit more tokens to get anywhere. And so we thought, could we improve this further? One thing we found is models aren't great at paraphrasing if you just ask them to paraphrase. And so an increasingly common thing that people do is to not rely on language models as essentially sources of randomness. Even though they're generative models, instruction-tuned models are often not that diverse. And so we basically want to inject external sources of randomness. And so our idea is pretty simple. We are inspired by a knowledge graph. And what we do is we look at a document, we identify sort of entities within this document, once again using a language model. From this list of entities, we sample random subgraphs. So in this case, we pick a pair like Da Vinci and the Louvre. And then we prompt the language model to synthesize the descriptions in this subgraph, right? So you might have a language model to say that the Louvre contains works by Da Vinci, right? And so now I've instantiated a piece of text that explicitly describes a piece of knowledge that's not explicitly described in the original document, right? So I've sort of surfaced an implicit relation into an explicit piece of data. And now I can train on this, and the model will have a much easier time sort of learning these facts. And this basic approach works quite well. This pink line is this sort of knowledge graphs inspired idea called Entograph, and it can just continue to scale to several 100 million tokens, exceeding sort of even GPT-4's performance. And GPT-4 here is the teacher model. Okay, and I think I'm short on time, so I'm going to skip a couple of things, and I'm going to finish on this last piece. I think synthetic data as a term has gotten a bad rap because it's used as a catch-all for all sorts of fanciful and impossible things. But I think one question that I think Emmanuel really sort of wanted to know was, why do we just get gains from not really doing very much? We're just rewriting data. Why does that help, right? So we built a little bit of a toy mathematical model in which we were arguing, okay, well, maybe a language model doesn't generalize very much. So all it does is memorize facts that appear explicitly in the data. And what we're doing is we're taking this original knowledge graph that exists in the document and repeatedly augmenting it, essentially making connections where there weren't before. And so as a generative model, we're just assuming that there's this Erdős-Renyi knowledge graph. And then what we do is, we take that intergraph algorithm of connecting different entities, we formalize it into this algorithm, and then we analyze the dynamics of this process. So where essentially we're picking two random nodes, and if there exists a path, we make a direct connection between those two. And maybe unsurprisingly, the limiting behavior of this process is that you connect, the connected components of a Erdős-Renyi graph. You can fairly precisely characterize the asymptotics of what happens here. Like, what is the scaling behaviors that we expect to see on the fraction of facts in the document that are fully sort of recovered by this process. And the point here is to say, you can't get all sorts of arbitrary facts. All we're doing is making implicit facts explicit. And then the last thing here is that, we're able to kind of characterize what the scaling behavior of this is, and the fit of this sort of predicted scaling roughly matches the QA accuracy that we get in our experiments, which is quite nice to see. Of course, this is a goodness of fit test and not sort of an extrapolation or a forecasting experiment. So I think a lot more work needs to be done to validate this. So, okay, the takeaway, I think it's going to increasingly become interesting to ask questions of data efficiencies for language models. We've shown a very simple way that the existing pre-training sort of paradigm is just incredibly data inefficient. Even by doing this very basic augmentation, like rewriting, you can get significantly better data efficiency. Of course, it costs you a lot more compute. So, so the two things that I wanted to talk about here today, right? One is on the inference time scaling. What is kind of the facts on the ground about our ability to use more compute at inference time? I think it's a really still open question. And then the other one is to maybe encourage you to think a little bit about kind of this data bound setting, which I think is going to be increasingly interesting. Thank you.
How sensitive is it to the different kinds of sampling schemes?
It's a good question. I don't think we have ablations on like node weighted versus whatever. We did uniform on the entities. And in fact, because of the scale that we have, we essentially almost enumerate every pair, and we get into random triples is what we end up with.
Thanks for the talk. The random graph process, the graphs actually represent something about the data or the model?
Yeah, the graph represents the data. So the starting state of the graph is the relations that are explicitly mentioned in the document. And then as we run the algorithm, we fill in extra edges, where each edge is an augmented, fact that we get when we pick those two entities and we describe them explicitly. And then we're asking, like, what is the limiting behavior of this process? Because that describes all the explicit facts that are going to be presented when you train them all.
The path to targeting after something to that.
The path to target means we pick two random entities and we're asking, is there a connection? Like, is the graph connected? Because if it's connected, then it's possible to describe what that connection is. If they're disconnected, then the model doesn't know what the relations are and it can't describe them out.
So I guess you're trying to cover the entire knowledge graph by adding more and more data. But I mean, if the model can actually reason, then they don't have to see the entire all possible combinations. As long as they know the knowledge graph, and as long as they can make some logical reasoning, they can actually like answer any questions about any path.
That's right.
So do you think like that will that be ever possible?
Yeah, I mean, I think the most pie in the sky version of this line of thinking is to say, well, really, what's the information theoretic limit of knowledge for pre-training? It's all the facts on the internet. But models can't learn all the facts and their implications on the internet because it's not explicitly presented to them. If we had sufficiently powerful, like long context reasoning models, then we could attempt to synthesize all these relations explicitly and train models on them. Like, I think that is, a really interesting like long-term direction. And also, I think what a lot of the people at these labs are thinking when they say things like, oh, we're going to use reasoning models to synthesize data, right? Like, these are the kinds of things I think they're often. Yes.
In your test and scaling plot, where is the teacher?
The teacher is, let's see, I think the teacher is somewhere down here, like near the model, but actually it's near the no intervention model, roughly.
Okay, so you scaled beyond the teacher.
That's right, with the weight tokens, yeah. But of course, the teacher could also probably scale beyond the teacher with the weight token. So it's unclear whether we're actually getting any capabilities improvements.
Okay, great. Let's thank Tatsunori.